Hello, could you hear me? Thank you. Thanks. We are starting. I'm just uploading the slides and then we start. Okay. I think we can start. So first of all, do you have any questions about the topic of the previous lecture, word level embeddings? Do you have any comments, questions? Okay. So actually, today we will proceed with the analysis of the embedding techniques. So how to embed textual content in vector representations generated by neural networks. The main goal is to design systems that are capable of transforming raw text into something that is manageable, that can be processed by machine learning models, either deep learning or not, and retain both syntactical and semantic properties within the text. These such a property is not satisfied by past solutions, which are, of course, more focused on occurrence-based representation. So they mainly capture syntactical relationship, also based on rule-based systems, so some domain-specific models developed by computational linguistic experts, but they are not general enough. They are not capable of automating the process of feature extraction, so they do need a manual feature engineering process. Conversely, we look for some more general solutions, data-driven solutions, which are capable to process end-to-end text, even in the absence of annotated data, and try to infer something, or at least allow to better represent data in a way that is suitable for computing text, pairwise text similarities. So given two pieces of text, we want to compute the similarity of these two pieces of text in terms of semantic similarity as well. So what we did last lecture was to introduce the so-called word embedding representation, which is, in a nutshell, a representation that maps each word in the vocabulary to a vector representation. So each word is associated with a high-dimensional vector of fixed size, and these dimensions, this representation will allow you to represent the input text in a unified latent space, high-dimensional space, and then on top of the latent space, you are able to perform some more advanced, some sophisticated analysis, like finding analogies, looking for synonyms, compute the similarity in terms of, so look for similar words. As we will see later on, there are plenty of applications in which this kind of models can find application. Now, today we will try to do a step behind. We try to compose word level representations to build sentence level embeddings. So what's next? So instead of considering single words as textual unit, we would like to generalize, moving towards a more general representation of the text. Of course, there are alternative options. For example, we can consider not only words but also n-grams. We can consider clauses, we can consider phrases. So there are many different options we may explore. We have seen together three main word level solutions, which are word2vec, fast text, and globe. Actually, fast text is not exactly word level, because it tries also to overcome the out of vocabulary issue by combining the representation of character n-grams, which are subwords. So not only entire words, but also subwords. Now, today, we will present the main approaches related to sentence embedding. These are let me say, the next step, which is not the last one, actually, because there are, as we will see next week, more advanced solutions called contextualized embedding, which let you build arbitrary representations of single words, or either single words or longer pieces of text, even paragraphs, by also embedding the information about the context, which is partly disregarded by the models I will show you today. So there are still some open problems that we are not capable of solving using sentence embedding, but we will try to address them next week by introducing contextualized embeddings. The models, the architectures, like transformers, like BERT, that probably all of you knows because are very famous, very popular in NLP today, belong to the contextualized embedding category. So we will, but we need, of course, some prior knowledge, some prior background in order to fully understand how these kind of state-of-the-art systems work. So first of all, we will introduce sentence embeddings as an extension of the word-level embeddings previously described in the last lecture. And then today, we will have an overview of a core element, of a key element of transformer systems, which is called attention mechanism. The attention mechanism is a feature of deep learnings, deep networks, that is being exploited not only actually for text, but also for other applications, like, for example, image processing. It is a general features, a general way to analyze, to attend to specific parts of the input content, of the sources. And there are some technical aspects that need to be, of course, known in order to fully understand how we can apply these mechanisms to textual data in an effective way. So in the second part of this lecture, I will try to introduce the attention mechanism without going into detail of how this will be integrated in the architecture. So regardless of the specific architecture we're gonna use to solve a specific NLP task, we will introduce in general what the attention mechanism is, what are the main functions, the main properties, how it works in principle and in practice, and giving also you some preliminary examples. Then, once you have the prior knowledge on sentence embeddings and attention mechanism, we can go on next week looking into the features, the main properties of contextualized embeddings, which are the further extension of this kind of models, including transformer architectures. Okay, so let me just outline the content, the topics of this lecture. Sentence embedding first, and then attention mechanism. Next week, we will introduce contextualized embedding, including transformers. Okay, I hope that we have time to complete all this part, at least most of the aspects. Moreover, next week we will have also a 3-hour lecture on 3-hour in-class practice on word embeddings. So my teacher assistant Moreno La Quatra will present you some overview some practical aspects, how to use word embeddings, how to play this with these systems, with this kind of textual representations, in order to be ready to go into the lab next week. So on Thursday, if I remember correctly, and do a practice work, a practice lab specifically devoted to word embeddings. You will actually you will try to apply both word and sentence embeddings in lab, but of course we mainly focus on the first one because they are more easy to use. So next week we will have 3 hours on Tuesday of in-class practice on word embedding, sentence embedding. Then on Thursday we will have a laboratory on these topics, and then on Friday I will start the overview of contextualized embeddings. Any comments or questions? Okay. So here you can see the list of representative sentence level embedding models which have been proposed to extend existing word level embedding techniques like word2vec, fast text, or globe. Today we will see what are the main features, the main properties of these systems, and how they try to incorporate the information at the sentence level. So first of all, why do we need to build a sentence level representation? Of course, when you have to understand the natural language, you can leverage the properties, the ways, the information provided by the text composition. So looking at single words only is of course suboptimal because you miss some higher level concept which are described, which are inherently represented by a composition, a mix of words. So you can, of course, abstract your analysis towards a more general representation of the text, of a longer pieces of text, moving from just a few words, like a word n-gram, so a composition of a sequence of words, to a more extended version of the text, like an entire sentence or an entire paragraph. How to combine such small textual units? So the typical case is to combine single words, extending word level embeddings, or either combining n-grams, charter n-grams, like on top of the fast text embeddings. You can build sentence level representations. So we try to, let me say, tune the word embeddings. We already know, word2vec, fast text, in order to be able to compose embedding representation of sentences. These compositions are not new because the subject of text composition is actually known from for many since at least the mid of 90s. So it's a quite old problem because most linguistic experts prior to the advent of deep natural language processing have already tried to build to study how to compose effectively text representation. But of course they may rely on rule-based models. They are very specific and are tailored to particular languages, particular context. So we want to try to generalize to find a way to learn in a data-driven way some representation that is general enough, that is capable of capturing semantic rules and not only syntactical properties. So of course, combining complex the elements, the items occurring in a complex expression is very important in natural language understanding. We do this in many different ways. the most trivial approach to combine textual units is the so-called bag-of-word representation. A bag-of-word is essentially a set, an unordered set of textual units. Like a bag-of-word is typically a bag, a set of words where the order of appearance of the words doesn't matter, and even the presence of multiple occurrences of the same word within the same piece of text is disregarded. So if you have many times occurring the same word, you disregard it. This is the very simple, the simplest way to combine words. You miss a lot of information, of course, because you are unable to capture the sense of the text, which is expressed by a specific ordering of appearance of the words. And you, of course, do not consider the term frequency, which is a key term in for example, in the TF-IDF representation, which takes also into account the local popularity of a word, of an item within a document, and not only the global frequency, which is the global frequency or the popularity of the item in the whole collection. So this is the very first way you can, the very simplest way to address this issue. But of course, it's not very smart. You can do something smarter by leveraging the already known word level embeddings. So let me say you have let's assume to have a word embedding representation already available. For example, some pre-trained version of Word2Vec on a specific on Wikipedia for the English language. Okay, I can take as input an arbitrary sentence or a piece of text and try to compose our sentence level representation by simply aggregating the word level once. Okay, so the idea is to combine word level representations. But if you look at each single word separately, of course, the network misses some relationships, word relations that are potentially relevant to embedding purposes. So our goal is to outperform the occurrence-based representation by building sentence and document level composition of text. We can approach this problem, we can tackle this problem by simply combining word level components. This is, of course, let me say, a baseline method we can consider. Of course, if the problem is extremely simple, is very simple, we can rely on vector representation, which are, of course, easy to find, which are less computationally intensive, at least for the training part. So this solution can be considered, even if we already know that the limitations. How to tackle this problem, as we've seen last week, when we consider, for example, the analogy problem. In order to combine words that are represented within the same latent space, the most common way is to compute the average. So you can, of course, apply any kind of aggregation function, but the average is for sure the most popular one, and the most appropriate in this case, which means this is a word, this is another word, this is the vector, the average vector representing the combination of the two words. Okay, you can approximate the sentence level representation of a sentence level representation as a combination, as an average of the corresponding word vectors, of the composing word vectors. What are the drawbacks of doing feature averaging? The main problem, of course, is that when you train the model, the word level model, you look at each word separately. So you have the word and the contextual window, which, according to the distribution hypothesis, tells you what are the words that are similar, that are potentially related to the target word. But of course, you miss a sentence word relation. You just have a partial, potentially incomplete view of the sentence level portion. You miss, of course, some dependencies, also because the window you consider you use to slice over the text in the self-supervised process is fixed size. So even if it is the same, even if you consider longer sentences, longer pieces of text, the size is always the same. Okay, it's not adaptive according to the length of the sentence. And then there is another issue which is not actually, which is only partly solved by sentence embeddings, and this is one of the key elements for the introduction of contextualized embeddings, which will be addressed later on, and is the word ordering, the position. The position of the words matters, because if I just change the position of the relative position of the words within the same sentence, the meaning of the sentence can radically change. Let's take a look to this example. If I say I'm going to study math instead of English, okay, this is completely different from the second one. I'm going to study English instead of math. Okay, two opposite meanings, but the same words. So just composing word level representation is not enough. We have to, let me say, encode. We have to push also the positional information in some way, to some extent. And the best way currently, the best way to do this is to exploit the attention mechanism. We will introduce after the break this today. This is not the best way. I mean, also the best, also the smarter, but also the most efficient way, as we will see, because the attention mechanism allows you to do the learning process with a high level of parallelization. So the high degree of parallelization, it's very, very efficient. It's particularly suitable for GPU-based computation. But prior to moving to attention mechanism and contextualized embedding, let's focus on sentence level embeddings. The approach, the general approach we adopt is to directly train a sentence level representation. In some cases, the sentence level representation is trained jointly with the word level ones. Okay, and whereas in some other cases you just focus on the paragraph, the sentence level granularity. The network tries to learn how to combine the word vectors, so it takes in input, of course, again the words in a piece of text, but tries to generalize the embedding representation to an arbitrary sentence. There are two different approaches, not really complementary actually. The first one is unsupervised, which means no annotation, no prior knowledge provided by domain experts, and this is the typical case. And we will see some examples of architectures. Doc2Vec is the very first one, the most, let me say, the most famous, especially because it has been proposed by the same author of Word2Vec, which is, of course, the pioneer work in this field. Then there are other architectures like Sentence2Vec and Skip-Through. We will see how that approaches work. And then there are some alternative solutions which rely on a different paradigm, a supervised paradigm. Supervised means that we already have some annotated data. More specifically, some annotated sentences, or more typically, some annotated pairs of sentences, which tell you something about what are the relations holding between pairs of sentences. These are particularly helpful in some contexts, but this is not necessarily effective because they work in practice only in some context, but are not necessarily portable to other ones. So what we apply here typically is a transfer learning paradigm. So you take a model trained on some annotated data, leveraging such annotation in order to improve the quality of the embedding representation. And then you hope that the same model you are trained is also effective in representing data in a similar context. But it is not always true. So it's something that we assume, we test, we empirically evaluate, but it's not necessarily true. Let's start from the very first solution, the first attempt to generalize word-to-vec. It is called doc-to-vec. In some cases, you will find this approach as the name as an alternative name, paragraph-to-vec, but the idea is the same. Okay, we are representing a vector in a fixed size vector, high-dimensional vector, not only the single word, but the entire sentence or paragraph. Similar to word-to-vec, the authors have proposed two different architectures, which are inspired, of course, from the skipgram and CBOW representation architectures that we already know. Let me just briefly recall. In the skipgram architecture, we have the target word, and we have a context window. The target word is centered. The window is centering into the target word. So then we have from 3 to 5. Typically, we have from 3 to 5 preceding words and from 3 to 5 subsequent words. The skipgram model, as an objective of the training process, is to predict, given the target word, predict the context word. So the words that are immediately preceding or subsequent. Conversely, the CBOW architecture has the goal of predicting, given the context, predict the target word. Okay, so the dual problem. We have already discussed the pros and cons. We have seen how to represent the input-output. So I don't want to repeat. I just want to make sure that you have at least a general idea about this architecture, because of course this is simply an extension of the skipgram and CBOW architecture towards a sentence level representation. The two solutions are called here distributed memory and distributed bag of word. These are the names that the authors have assigned. Let's start from the first one, distributed model of paragraph vector. This architecture is very, very similar to the skipgram model. No, actually, not exactly. Sorry, we start from the CBOW. I did a mistake. It's similar to the CBOW model, and the idea is to take as input the words within the contextual window and try to predict the target one. In the CBOW architecture, the goal is to predict the center word, which is the target, which is assumed to be the target. Here, we have two main differences with respect to the CBOW architecture working at the word level. The first difference is that the target is not the center word, but is the next word. So we have the sequence of words, the cat set on the table. On, if the window is this, you predict the next one, not the one in the middle. Okay? So you try to predict the next. Missing the information about you have the information about the preceding words, but not the information about the subsequent ones, because the words after on as these are disregarded by the contextual window. Secondly, we have this element colored in orange, which is the, let me say, the most important part, because it is called paragraph ID. It is a special word identifying the paragraph to which the words in the context window belong to. Okay, so you index the input text to each paragraph, to each sentence. You assign an ID, a unique ID, which is used then to specify as input when you consider an arbitrary context window sliding over the input text. So when you have a slice, then you are here considering this piece of text, the cat set. You are looking for which is the paragraph this piece of text belongs to. It belongs to paragraph with ID 10. So this is an artificial word telling you, okay, this is the paragraph, these words belong to paragraph number 10. Actually, behind the network works exactly as the word-to-vec one. So the idea is to replicate in some way, in a very similar way, the word level, the word-to-vec architecture. But these are the presence of this artificial word denoting the paragraph, the membership to a particular paragraph, tells to the network, okay, you are in this context. So you have also the information at the sentence level. So you mix, let me say, word level within the current context window and the sentence level information associated with this, the words in the context window. You miss, of course, as word-to-vec, all the information about the words outside. But if this piece of text belongs to a longer sequence of a long paragraph, and there are some words, some other words here, then in the training phase, you will consider also samples generated by multiple slices over that paragraph, which have the same paragraph ID. So they have the paragraph ID in common. So in other words, we are trying to keep a memory of the paragraph membership of that slice, of that sample, in a way that allows the network to learn something about the sentence level representation. So the paragraph information is embedded into an artificial word, providing you as a memory information about the membership within a particular paragraph. Okay. So every paragraph is mapped to a unique vector, which is, of course, the output we are aiming at achieving. Each word is also mapped to a unique vector because this architecture is specular to word-to-vec. The paragraph can be thought as another word, as a special, let me say, artificial word, which acts as a memory, remembering either what is missing within the current context or the topic of the paragraph. Is missing because the paragraph is typically longer than the context size. So something outside the context window can be relevant as well to characterize the sentence, the embedding generated by the model. And even, of course, indirectly, it influences the prediction here, because you are, of course, this representation is generated by self-learning on a particular task, which is predicted the next word here. Is it clear? Okay. So the prediction task is similar, not exactly analogous. So this term is not, maybe it's a little bit misleading. I will have to fix it, because the target is different. We want to predict not the center word, but the next word, without considering, as written here, the subsequent words. We consider only preceding words only. And the surrounding context is encoded by a paragraph ID, which summarizes all the missing information within the paragraph. Then you apply an average or pooling or a concatenation to predict. So you have the network combines the intermediate layer and provides you the outcome you expect. Of course, here the size of the context is again fixed, so you have no way to adapt the size of the context. It's not adaptive, and this is of course one of the limitations, which will be also again overcame by the architectures like contextualized embeddings, which rely also on attention mechanism. The paragraph vector is shared across all the context within the same paragraph. So if you generate the samples for the training phase, you slice with the context window over the paragraph, and of course, whenever the piece of text belongs to the same paragraph, they share the paragraph ID. Then a question could be, what happens if the slice is in between? You typically disregard this, because it would be like a in-between context window where part of the words belong to a paragraph, and the remaining ones belong to the next one or to the previous one. So it's not considered by this architecture. So you build samples within paragraph, but not across paragraphs. Okay, you miss this kind of samples. But please. One word, because the problem you are considering probably is a more general one, which is called, it is addressed by other kinds of architectures called language models. We will see this next week. It's a different case. So here the one, just one word, as in the word-to-vec case. Here in the distributed Lego word, you predict again one word at a time, but the words in the context. So you have the context window here. This is more similar to what you say. So given a paragraph ID as input, you are going to predict what are the words that occur within the context window. Okay? So the entire context content. You know the paragraph, and you try to predict the words in the context. At each iteration, okay, you sample the data using also, you take also random words sampled, because of course you have to generate the samples. You have to generate samples where, like in the self-supervised scenario, you have to generate samples where you know the input, you know the output, and the network learns how to tackle the problem. And so what is the input? The input is the paragraph. The output is the context window. So you can we don't generate actually all the possible cases, not just simply, but you randomly pick some key just to avoid oversampling. So this is just a technical detail to reduce the complexity of the learning process. Here you can find an additional reading. So this is the original paper. You can read through it if you want more technical details or if you have some curiosity about this. Even if it's not the most recent solution, it is still quite used because it's simple. It's simple yet effective. Of course, it's not effective as state-of-the-art models like transformers. Then, an alternative approach is called sentence-to-back. It is again unsupervised, so you don't rely on any human annotation. You do the training phase. You build the training data set in a self-supervised way. This approach relies on fast text representation of the text. So you consider character n-grams instead of words. So it's more like an extension of fast text instead of an extension of word-to-back. The idea here is to extend fast text using an architecture which is similar to CBOW in order to build a sentence-level representation of the text, where, unlike the previous solution, the doc-to-back architecture, we consider here the entire content of the sentence instead of a fixed context size. So we adapt the size of the context to the sentence, to the length of the sentence, which is not fixed, which is not known in advance. You do sentence tokenization in order to split sentences, and then you consider the context window as an entire context, the entire sentence. And then you train both n-gram embeddings and their composition, which is the main target of our application, which is the sentence-level representation. So here is an example. The CBOW architecture has the goal to predict the center word of a context window given the context word. So given the preceding and the subsequent ones. So for example, if I have this sentence, the quick brown fox jumps over the lazy dog. This is a typical sentence in NLP. A toy example in NLP, you will find this many times. The goal is to predict jump, okay? But you do it not only on a fixed size, but you include in the context the entire sentence. You rely on a word level, not only on a word level representation, but also subwords, as in the case of fast text. So you are also able to overcome, at least partially, the auto-vocabulary issue, which is still present in doc-to-back. So this is an important point. So if some words are missing, you are not able to encode them. So you miss the information as in word-to-back. So doc-to-back has the same limitations of word-to-back in terms of representation of the text, auto-vocabulary issues, negative sampling, so whatever kind of technicality. The technicality is the same because practically the architecture is very similar. Here, you rely on fast text, so you partly overcome this issue. You consider the entire sentence here instead of a fixed size context. So this is the fixed size of fast text. you enlarge this window by also including the extra words belonging to the same sentence. And of course, this is, in this case, in this particular case, this is particularly beneficial because you for example, you correlate the dog with the, you can find some words that are potentially correlated with the target one. And then, of course, you have a matrix representation here of the matrix. You can find here. So this is actually a detail of how the matrix form is computed here to generate these intermediate steps of the learning process. You have to, again, predict the missing word, working at embedding level. So here you have, again, a vocabulary including both words and subwords. So it's not simply n-gram level focus, but also you include also the entire words. You apply negative sampling as in the case of word of fast text. So this is the same trick to overcome the presence of the imbalance between positive and negative samples, because of course the chance to find randomly a positive case is very, very low, whereas the likelihood of negative cases is very high. So you have to do negative sampling in order to rebalance. And that's it. So it's not, so the key point are those that are mentioned in that I mentioned before. So first of all, largest context window, not fixed size, sentence level, and fast text, so n-gram, character n-grams included in the representation. Target, not the next word, but the center one, so as in the original SIBO case. Skip through. This is yet another solution. Of course, I mentioned just the most popular one, but maybe there are still other that are not considered in this presentation. This is again unsupervised. It is interesting because it relies on a popular encoder-decoder architecture that you probably know from the previous courses of the data science course. So the encoder-decoder tries to reconstruct some data in input. So you have the encoding phase, which transforms some input, which can be also fixed variable size, into fixed size encoded vector. Then you have the context, which produces then the output, which is decoded. So you have a decoding phase. And for the encoded version, you produce an output, which is again a variable length sequence. Now, how to leverage such a encoding and decoding process in order to solve the sentence embedding task? We can do this. So the idea is that sentences that share the same properties, even at the semantic level, which is the most important one, are mapped to similar word representation. So this is this drives our idea, which works like this. So let's skip the details here, which are more technical details. Let's try to focus on the main idea, looking at the running example in the top part of the slide. We have a target, as input, we have this sentence, x in position I. A given sentence, xi, is encoded together with we have two, the architecture is composed by an encoder and two decoders, actually. Given xi, we have a previous decoder network, which tries to reconstruct the previous sentence. And you have a next decoder network, which tries to reconstruct the next sentence. Okay, so given the sequence of sentences in the original text, if you have an original paragraph including 3 sentences, x minus 1, I minus 1, xi, and xi plus 1, you are trying to reconstruct the original sentences, the previous and the following sentences, given the central one. So the idea is very similar to those applied by skipgram at the word level. So if you think about, if you recall the skipgram architecture, what you do is to consider the center word in a context window and try to predict the preceding and the subsequent ones. Here we are working at the sentence level. So instead of tokenizing the raw text into separate words, we tokenize the sentences within the paragraph. Given a target sentence, xi, we want to predict the previous one, the immediately previous one, and the immediately subsequent one. I minus 1 and xi plus 1. Okay? So it's, of course, it's a narrow context window because, of course, paragraphs of text are not expected to be so long. So you're not expected to have so many sentences before, so many sentences after, even because maybe you miss some correlation. So exactly the previous sentence is likely to be correlated to the next one. This next one as well, but you may miss. You have weaker correlation with faraway sentences. So this is the key idea. How to implement this? They have implemented this solution using some recurrent neural networks, both for the encoder and for the decoder. The recurrent networks try to leverage the sequential nature of the input text. So you take a sequence, you learn how to reconstruct the sequence, and you do this both for the previous and then for the next one. Of course, if you have a high complex data collections, large data collection, this task is much more computationally intensive than before, because you have both encoding and decoding, two decoders. So it's potentially critical from a point of view of computation. The doc2vec, of course, architecture is much simpler and, of course, much cheaper from point of view of computational time and resources. How to model the text? So given a tuple of three sentences in a row, which are contiguous, so one after the other, si minus 1, si plus 2, you separate the sentences from a technical point of view. You have this token which tells to the network, okay, pay attention, this is a separator. So we need some artificial way to separate sentences reflecting our tokenization. So of course the tokenization is needed, because otherwise the network is not capable of understanding how to build your context. So you do need this separator, you do need the tokenization in order to address this problem. Okay, so as you can see here, you have a sequence. This is encoded, and you have to decode both this is the end of sentence token, and it separates the current sentence for the preceding and the current sentence for the subsequent. Okay. Okay, so this concludes the overview of the unsupervised approaches. These are all rely on the idea that we have no prior knowledge about the semantic level relationships. This is not always the case, because in some particular context, you do have some hints on how the sentences are related to each other, especially on what is the direct relation. So one is the cause and the other is the effect, or one is the hypothesis and the other is the verification. And this is the case for InfraCent, which is a supervised approach designed by Facebook researchers. And this approach is a universal representation of sentences based on a collection of annotated text called Stanford Natural Language Inference. And this is quite a large set of human-generated pairs of sentences written in English. So this means that it's not portable to languages other than English, unless redoing the annotation phase. Maybe some other researchers have tried to extend, but this is, of course, the benchmark here. They have tried to label. So, of course, if you have an annotation, you have labels. If you want to drive a supervised process, you need a target. The target is the label, which tells you whether the sentence pair is the sentence relation of the pairwise sentence relation is either entailment, contradiction, or neutral. We can see an example here. These are the examples of entailments. For example, if I say the text that contradicts an hypothesis, so one is the hypothesis and one is the contradiction. For example, giving money to a poor man has no consequences. This is the hypothesis. The text is a contradiction. No, if you help the needy, the God will reward you. So it's a kind of semantic mapping between two sentences, and it's directed relationship, not undirected, because you know that this is one is the hypothesis and one is the consequence. Okay, so some directed relations. There are different kinds of relations that like positive or non-neutral. Like positive is giving money to a poor man has good consequences. This is similar to the previous case, but in this case, if you help the needy, God will reward you. So this is a positive entailment. So they have tried to build, with the help of linguistic experts, a training set consisting of pairs of semantically related sentences, and they try to train the network in order to build a sentence-level representation that reflects this kind of text-level correlations. Is it suitable for, is it good or not? It is useful or not compared to, for example, unsupervised approaches like doc-to-vec, sentence-to-vec? The answer is depends. It depends on whether the context of the training context, the type of sentences, the type of text you consider is likely to be similar to those you are using actually in your application. So this approach is strongly relies on a, let me say, transfer learning approach. So the idea is to, okay, learn something that works quite effectively, at least is accurately describes something in a context within a particular context, and try to do the porting, to port it, to transfer it to a similar context. So if you envision a context where the trained model is potentially similar, as some kind of similarities, then okay, do leverage it, do exploit such a representation. Otherwise, probably it would be more convenient to rely on to address the problem using unsupervised models. Okay, here you get. Okay, this is just the combination of the two sentence level representations, and that's it. Nothing special about the architecture. They leverage an Lstm representation, which is used to, again, to train a hidden representation of the architecture. They also explore the use of an alternative architecture called GRU, which is again tailored to sequential data. You perform max pooling to find the maximal value. So this is just a technical detail about the architecture. And the sentence the sentence representation is achieved by looking at the last hidden vector, because it's like of it's a cascade of multiple layers, of multiple hidden representations. So the last one is those that returns the output vector you are going to use. So here is the representation. It tries to capture here to some extent also the position of the word within the text, but since it relies on a Lstm architecture, it suffers from the long-term dependencies. It misses long-term dependencies. So this is, of course, suboptimal when you have to deal with longer pieces of text. And of course, this problem can be addressed more effectively using other solutions, like, for example, solution based on attention mechanism that we will introduce later on. So the main cons here are the common issues of LSTM models, like vanishing gradient and long-term dependencies. Okay, here they have tried to address the use of self-attention, but this concept is not, we have not introduced it yet. So this is the topic of the second part of this lecture. So I propose you to skip this, and then we go back and recall this at the end. Okay. So I think we can. Let's skip this for a while and see. There are also some other attempts to do a similar job. One of the is not. So the competitors are the most the largest tech companies like Facebook, Amazon, Google, Microsoft. So the previous solution was proposed by Facebook and leverages the Stanford language dataset. Here, Google has proposed a similar solution where they try to embed the information using some pairs of sentences which are not just hypothesis and contradiction, or something that is cause and consequence, but they are simply semantically related sentences. Okay, so what changes here is actually the kind of semantic annotation you made in the text. This is the most interesting aspect of this approach called the universal encoder. Okay, so I don't go into, of course, if you are interested in, you can take a look to this project. It is open source, so you can access and download it. Actually, compared to the previous one, the key property is that it relies on a different kind of semantic annotation. So instead of having causality, some relation, some directed relation, here you have some undirected semantic relation between a pair of sentences, which is not obvious which one is the best. It depends, of course, on the kind of problem you are going to address. Okay, any questions? Okay, so I think we can have a break now, and then we switch to the attention mechanism part. Okay, I think we can restart. My teaching assistant, Dr. Moreno Acquata, has also created a Discord channel for exchanging information, issues. He has already informed you or not? Yes, okay. You should, you can write your doubts or comments or any issue on the channel, or of course you can contact me, especially for the technical part. So problems with the code, problem with the software, problem with the laboratories, you can inquiry Moreno directly using Discord. Then after, during the development of the project work, we will also use Discord to create separate channels devoted to each group, if need be, of course. If you need if you have some specific questions, they should not be sent out in broadcast, but they can be shared through a dedicated channel. Unless they are general purpose questions that can be also useful for other students. In that case, of course, you are free to use the broadcast channel. We are still finalizing the topics, the choices of the projects, so I will keep you updated in a very short time. This week we have not still we are not finalized the work because my teaching assistant is abroad, so it's difficult to keep us connected to exchange ideas. But we will keep you updated as soon as possible, even especially for the survey, to know exactly the composition of the groups, what are your preferences. So this stuff, we will do it as soon as possible. Our plan, as I told you during the first lecture of the course, is to assign the project works by the end of October, or at most in the early November. So of course we have time. We are not in a hurry, but I would prefer to know, especially what are the logistic issues, in order to solve them as soon as possible and avoid issues or misunderstandings. Any questions or comments? Okay, so now we have presented the main sentence embedding architectures. Now we move to another topic, which is partly related to, of course, which is the attention mechanism. It is a mechanism used for learning from data. So it's a feature of many deep learning architectures, both in NLP and in other contexts, including images, videos, or multimodal learning. How many of you are already aware of what the attention mechanism is? At least some idea. Okay, 1, 2. Okay. Because of course this is a general topic. This is covered also by some more broader deep learning courses, not only NLP courses. It is especially relevant to NLP applications because the state-of-the-art architectures for NLP, called transformers, heavily rely on that approach. So the most famous paper in this topic is entitled "Attention is all you need." So if attention is this, we will present this. We will further describe the architecture during the next lectures. Today, I just want to give you a preliminary introduction to the attention mechanisms. So instead of going into detail of the NLP architectures, I want to discuss it more in general. So broadly speaking, just to have a big picture of what are the potential and the limitations of this approach. Okay. So let's start. What we are going to do is to introduce the intuition first. Then we have some preliminary example. We see how to jointly train and what are the first attempts to use attention mechanism, and then we will go into details. Actually, we will have also a detailed formalization of the attention mechanism. So let's start from the intuition. First of all, what is the idea? What we want to do? The idea is to focus the attention of the network on specific parts. So as your human brain does, you actually, when you have to accomplish a task, you are not analyzing actually all the aspects, all the whole set of data you have, but you specialize your brain to focus on specific parts which are more relevant than other to address that issue. For example, the most typical case, which can be explained by example here, is object recognition or image classification. Let's assume to have an image. You want to know, you want to label, to annotate the image with indicating which are the objects that appear in the image, or which is the category from a set of predefined categories. You can leverage the attention mechanism to put the emphasis of the network learning process on specific parts of the images, which are more relevant than other to address the task. Okay, so instead of exploring the whole set of content and assuming that all input data are equally important, which is actually not true, you try to find out which are the patterns, which are the features that are most useful to attend to in order to solve the problem we are going to address. So this is a general task which can be tailored to images, to videos, or of course to text. It is particularly important for text because the state-of-the-art architectures heavily rely on this mechanism. What are the tasks that we are going to address here? Mainly text classification, machine translation, question answering. So most of the NLP applications, not all, but most of the NLP applications that I presented you during the NLP overview, initial NLP overview, are currently addressed using attention-aware networks, or at least also being addressed using these networks by achieving state-of-the-art or very promising performances. So what comes from the empirical evidence is that these kind of networks are on average outperforming the traditional recurrent networks. So they are more efficient to cope with specific kinds of textual data, which we will describe now in this presentation. So in a nutshell, is particularly helpful when you have to cope with long pieces of text where you miss longer-term dependencies. So you miss dependencies in the text that are not related to immediately after or immediately before occurrences of words or n-grams. But when you have to capture a more higher level, more complex relationships, for example, if you have to detect the sentiment of a text and the phrase is not well easily to interpret. Is the structure of the phrase is complex, or for example, when I use, for example, for example, the I missed the term. Like if I'm using some strange form, some senses of words to express my feelings. For example, if I am sarcastic, okay, sarcasm detection is a typical case of sentiment analysis where you need to capture the dependencies in the text which are not classical, not traditional. So just looking at the simple natural order sequence of appearance of the words is not enough. So here you can see what we get. This is a saliency map which shows you the connections between words that are influencing particularly the recognition, the classification of other pieces of text. So I will show you some graphical representation which summarize this point, which we will denote as attention score. The attention score is, in a nutshell, an indicator of what should I attend to, which part of the text should I attend most, and it is similar to this patch surrounding the most relevant object, the most relevant subject in an image. So I want to focus the attention of the network on a particular patch or a particular shape within the entire image without avoiding wasting computational resources, time, and losing performances while considering the entire images. And as in like in CNN, so convolutional neural networks, which are typically used to solve image processing, image classification, you do not focus on a specific part, which is potentially more relevant to classify that image. So in this case, we apply a similar approach, where the patterns that are most relevant to attend to are analyzed at the word level. Okay, so the idea is to mimic the human reasoning. So when you do classification, when you classify an object, when you look at a video, watch a video, and say the category of the video, you segment the video. With this kind of all these kind of complex tasks are commonly accomplished by a human by focusing on specific portions of video segments, specific video portions, or specific fragments of audio track. So they try to specialize the model on particular most relevant parts. And this is exactly what the attention mechanism does. Recognizing specific regions which are instrumental, for example, for classifying a subject. Here we have extrapolated the main subject, and we have removed all the background, which is not relevant enough. What we do, for example, in image classification, as I told you, is to process the entire set of features and doing the optimization, the gradient descent using a set of convolutional layers. We can, of course, repeat the process on the entire images, but this results in a poor performance and also in a waste of computational resources. We want to build a network that dynamically focuses on specific features which are automatically derived by the network. So we no longer want to rely on human-generated, human-selected features. So here we have applications like sentiment analysis, hate detection, misogyny detection, sarcasm detection, where the structure, the way, the form of the sentence is particular, is peculiar, and most of the existing solutions are not performing really well. So in that case, it is particularly helpful to rely on alternative solutions based on attention-aware networks, where the gap in performance is particularly significant. The attention score is, in a nutshell, is a distribution of probabilities which sum to 1 and tell you exactly what is the key element that you have to consider. In that case, we are considering a piece of text. We are doing sentiment analysis. We have to weight the importance of a word with respect to the ability to discriminate between positive or negative sentiment. So here, okay, we are in a very in excellent case, where a corner case where you have 1 and all zeros. This is not always the case. We have probabilities, but that highlight some parts of the text that we are willing to attend to. Okay, so the very first attempt to use the attention mechanism in natural language processing was made in machine translation. Okay, it was work on published in 2014, 15, sorry, and it basically relies on encoder-decoder network, where the network, the encoder of the networks reads and encodes the source sentence, and the encoded version is a vector of fixed size, as I described in the introduction of this course. Then you take the context vectors and you produce with the decoder an output translation from the decoded vectors. Both the encoder and decoder are jointly trained to maximize the probability of a correct translation. But of course, we have some problems while coping with real pieces of text. First of all the necessary information of a source sentence need to be compressed in a fixed length vector. So basically, while encoding the source text, you are summarizing all the key information in a fixed size vector of numbers, and this may result in a partly lossy representation, because especially when you have complex and long pieces of text to translate. So when I have very short pieces of text, it can be not, the loss can be limited, but we have long, complex and even complex in structure and long pieces of text, you may miss relevant information. So the problem is to cope with long sentences, and you can what we get from the empirical evidence is that the training corpus consisting of longer pieces of sentences to translate usually get worse performances. So how to cope with this issue? The solution was, in this case, try to start to applying an attention-aware mechanism where you align and translate jointly using, in the alignment step, you attend the most significant portion to translate. So here is the very first application where the encoder was a bidirectional recurrent neural network, and the decoder emulates a search in a text, so the so-called information retrieval task. Given a search query consisting of set of words, we look at the sources in a collection of documents that are most pertinent to a query. So basically, the decoder tries to find which are the pieces of text that are most relevant to the translation step. So each time the model generates a word in translation, it searches for the other words in other position in the source, which include the most relevant information. And this is like building your adaptive contextual window. So not a fixed, but adaptive, picking only the most relevant pieces of text to attend to. Then the model predicts the target based on the context vector associated with the source and the previously generated target words. So you include a contextual information beyond the traditional context source, which is something like, okay, I have a piece of text. I want to translate that piece of text. I want to know whether that piece of text or even its word-level content is somehow related to other pieces of text I'm not going to consider. I include them in my context-aware representation, and I use it to decode in the decoding phase. So it's an attention-aware decoding, okay? Which is the very first attempt to leverage attention mechanism in NLP. Of course, there are other works that have tried to use attention-aware networks, but not in NLP, like images or other contexts. This is the, let me say, a pioneering work in NLP, which is quite old. So it's almost 8-9 years ago. So it's not new, but the way you embed, you leverage the attention mechanism in architecture as being adapted and reused in a smarter way after some years in 2019 with the advent of the transformer networks. So here is the architecture. This is very similar to the architecture we have seen before for the sentence embedding, as you can see here, because it's again a cascade of recurrent neural net, bidirectional recurrent neural networks, as usual. And then you combine in order to decode. And here are the hidden states. Consider this contextual information, see, which is the really important part according to the attention mechanism. So the context information comes from other parts in the text which are not defined in the fixed window. Okay, so you pick something outside depending on the attention score. Something like, okay, I look at the words immediately preceding or immediately subsequent. Okay, that could be not enough. I know it. So I will also consider the words that are top relevant according to the attention score. So even if I have a word that is relatively far away as a position in the sentence, so it's not included in the standard context, but it's relevant according to the attention score because I search only those words, not the other. I pick those words and I consider them as well in order to improve the quality of my sentiment analysis process. Here, the task is not sentiment analysis, is not machine translation, but the key idea is the same. So the idea is to build a context vector, which depends on the sequence of annotations to which the encoder maps the output. And the annotations are actually not human annotation, but are computed by the network using this attention score. These are the attention scores, which contain information not about a single local context, but about the whole sequence. So we are including the information about the whole sequences, embedding what is a global context, picking out picking just the key most important ones, so those that have a highest attention score. So we strongly focus on the parts that are surrounding the words, and this is a function which is a linear function, which is a linear combination with this parameter a alpha of the outputs of the recurrent neural networks in the cascade. This function allows you to return also distribution of probabilities. So as I showed you before, in the attention score, I have some numbers here, which are actually probabilities. So these are probability. This is a distribution of probability. This sums to 1. And these are exactly the attention scores that I have here. So the alignment model tries to estimate how well the inputs around the position J and the output at position I match based on a state Si minus 1. So we are trying to describe in a better way what is the context that really matters to select the output. Okay? So here we are at position I. We consider what is the context of I and how well the position J contributes to that kind of context representation. Now, of course, this is the general idea. This is actually the very first work. Let's try to formalize it better. And because it is really important to understand how transformer networks work. The attention mechanism relies on the idea of search, and we try to better understand why does it hold. So the idea is to identify within a text those portions that are most relevant to attend to. So, and we reformulate the problem as a search task. So yeah, given a piece of text, I want to find which are the pieces, the words that are most relevant to attend. And the input text, which can be also modeled as a single words, or even you can generalize, is a query. The query will be, we try to match the query with an index called key, which tells you, okay, this is the query is most similar to that particular key, and then you have to return the value corresponding to that particular key. So we extract the features that have highest attention by using this search mechanism. So we have three items, basically three items: the query, the key, and the value. We define the query according to the content we are going to describe, the current position we are going to describe, typically a word or even a combination of words. Then we compute the similarity between the query and each of the keys in the indexing my source data. Then we look for the most similar words in the document which correspond to the keys that maximize the similarities with the query. And then we return the values associated with that keys. So the first step is to compute the similarity between the query and each of the keys, because I don't know in advance which is the key, in which position the key, the most relevant keys are stored. Then, as when you open a book, you want to know something. So the query is known, is human driven in that case. you scan the index of the book in order to find which is the page at which the chapter of interest starts. With the key here is the position in the index. The query is your human query, and then the value is the content of the book chapter. Okay. You extract the values, so you go to the corresponding page and pick the content of the chapter of the book that you would like to read. So let's start learning what we mean with self-attention. The self-attention is a mechanism that tries to pinpoint which are the most relevant features in the input data. We have an input sequences of words, so we analyze text at the word level. We encode also the position of the words because, as you know from the previous discussion about sentence embedding, we know that positions matter. So in considering the position in the analysis of the sequential text is really worth, because we are able to overcome the issues related, for example, to sentences that have or pieces of text that have the same composition but different order, and the meaning of the sentences are completely different. So we have a sequence of words, and this is the corresponding word embeddings. We have the positions of the words here. We want to get some position-aware encoding, which tries to combine the original and the embedding of the word, this is regarding the position, and the position encoding. So we add position information in order to understand, also to make to take into account also the natural order of the words in the sequence. So in this way, we encode also the information about the position, the relative position, which is not available in the previous solution. For example, in a sequence embedding, in sentence embedding models, we typically rely on recurrent neural networks, which take the sequence without explicitly indicating the relative position of the tokens. So in that case, you provide data sequentially, one word after the other. And this is also computationally intensive, because you need to do several iterations, sequential iterations, so that the computational time and the computational resources are higher, because it's not inherently parallelizable. When you have to iterate using a recurrent neural network, you have to feed the input in a sequential order, to keep the sequential order, to have to store the memory about the past, and you cannot feed the data all together. So you cannot disregard the sequential order, because you miss the key property of the recurrent model. Whereas in this approach, you can feed all the information together all at once, because you already embed the position of the token level items, the word level tokens, directly in the representation. So getting a position-aware encoding allows you to parallelize the computation, getting much better performances. We will see this better later on, because we will compare the performances of transformer, for example, with more traditional recurrent networks like Lstm. So we see that the gap in performance is dramatic. It's very, very significant, order of magnitude. So it's not not only more effective, but also more efficient. Okay. Now let's consider the three elements we are going to focus on. we consider positional embeddings. We combine them linearly and produce an output, which is the query. Actually, the query in our approach is with a self-attention mechanism. The query is the input tokens as themselves. So you don't need a human-driven annotation to provide queries. The queries are self-supervised, self-generated. So you reuse the content of the input to generate the query, encoding also the position, and you do the same for indexing the content in order to understand which portions of the input are correlated with each other. And the same for the value. Actually, in the simplest cases, for example, for transformer architectures, the key and the value are the word itself. So are exactly the same. But this is a more general representation because, again, in the retrieval case, you can define a query as a bunch of words. Like if you type a Google query, then you get an index which corresponds to one of the top relevant, for example, links returned by Google. And then if you click, you get the value which corresponds to the content of the retrieved web page or word sources. So this is a simplification of the query retrieval mechanism. The self-attention mechanism needs to define a query, define a key that describe the content, even those that is not exactly close to the query. So if you have the words in the query, you can look at just the neighborhood, the immediately preceding and immediately after. But in that case, you get a fixed context which misses potentially relevant information which are far away. So the problem is that when you have longer pieces of text, when you have uncommon structures, syntactical structures, you miss relevant information. So the idea of a fixed content is not enough. So you need, in order to go beyond, you need a way to define the query, just picking the words, and encoding the position and combining the encoded embedding and the positional embedding together with a positional where embedding, both for the query and for the keys. And then you compute the similarity, which is the way to match the query with the key. Okay, as if you are interested in if you are reading a book or an encyclopedia, which is a long index, you look at you read through, you peruse read through the index, looking at the keywords that are most pertinent to your search. When you find them, you maximize the similarity, so that you move the corresponding content going to the corresponding pages. So, as in the word embedding case, the embedded information, which are vectors corresponding to either the query or the key. So you have vectors of numbers. That vectors are fixed size vectors like word embeddings. They can be compared using the standard dot product, so the cosine similarity, which measures the angle in between. So it's not related to the magnitude, but to the angle. Okay, these are vectors in a common space. So you can disregard the relative position in the common space and measure the angle in between. This operation is quite efficient because you can compute it just using a simple dot product. So it's cheap from a computational point of view. You have to repeat such operation for every possible key, because you don't know in advance which are the keys that are most relevant to your purposes. So you have a query, you compute the similarity between the query and each of the candidate keys, and you get the attention scores. Then you have to apply softmax function in order to get an attention weighting scores, which are basically probabilities. So for each of the tokens that are potentially describing your, let me say, adaptive context, you assign an attention score, a probability. So 0 for a particular word, 0.1 for another, 0.5. So you have different probability of being actually relevant, and this probability is simply computed using a softmax function we already know, which is computed over the dot product scaled, but which is just a simple mathematical formulation of the weighting function. So you get probabilities described by a weighting attention score, which consists of a probability distribution for each of the input queries. So for each of the input words in the text. This holds for the self-attention. So given a word, you have a distribution. Of course, the distribution here maximizes the probability if you consider the word as itself. So if this is a query, this is the key, which given a word, a particular word like tennis, which are the words that are most relevant to attend to? Of course, tennis is the same word. Okay, it maximizes the cosine similarity by construction, so not really interesting. But then, which are the other words that you are willing to attend to? Ball and serve, because these are the words, the keys that maximize the similarity with the query. These are probabilities 0, 0, 0, 1. Okay, this is not. Don't forget this. You have different probability values returned by the weighting function, and you can retrieve, as in a search engine, you can retrieve the words in the context in a broader sense, which are the words that are most likely correlated to, and are, of course, for tennis, these two, for ball, these two, for serve, these two, and so on and so forth. Okay, so you don't rely on sequential order processing. You don't need to feed data in a sequential order, so you have a significant increase in performance from a point of view of computational performances, and you also have an increased capability to consider dependencies, text dependencies that go beyond a fixed size context definition. So even long-term dependencies neglected by traditional LSTM models. LSTMs often, or recurrent models, often suffer from the presence of dependencies between faraway words. If the two words are correlated, but they are very far away, one at the beginning, one at the end, most of the times you miss that correlation for the gradient vanishing problem or for the long-term dependencies vanishing. So even if you use some smarter solutions, some smarter architectures like LSTM, you still can be in trouble unless using more effective solutions like the attention mechanism. Okay, so just to recap, we have the query. We multiply the query with the keys. You get the attention. Sorry, please. Because it's simple, the simplicity. Because it's not the only option. I agree with you. There are also other functions to implement this. The attention score, I show you in a minute. Oh, here is just to combine the positional encoding with the token embedding. Okay? You have to combine the positional encoding is here. It's not easy to capture here. You have the encoded version of the word, which is combined with the positional information. You have to combine the two in order to get this position aware encoding, which corresponds to, which is the driver for both queries and keys. And then you compute the similarity between the two. Okay, then, given the attention weights you get, you have to return the values that maximize the attention scores. And here is the output. Okay, you extract the features that are latent features, maximizing the attention. So it's a way, it's an adaptive way to extract the features that better describe the context of a word. Okay? And it's the same idea as we have shown before in the image. If you get the image, we want to extract the patches in the image that are most discriminating for tackling a particular task. Like, for example, to classify the image as a bird or as a car or as whatever, or human. How to define such contextual features? You do this using the attention mechanism. So this corresponds to what we have seen in the beginning here. This border, this corresponds to the attention. Okay. This is very important because otherwise you can get the point about the architecture. So what we are trying to understand here is the intuition behind the attention mechanism, which is of course fundamental in order to understand how the network works. Okay, so each head we can build an architecture composed of multiple heads, where each head is basically a self-attention head. So these are what I have described until now can be considered as a unit, a head of your deep network. We can build a stack of multiple self-attention heads, and this can be a way to combine either multiple patches. So if you have an image, you have an image. In the image, you can identify some pieces of the image, some portions, some regions that are relevant. But of course, depending on the complexity of the problem you're going to address, the number of relevant regions can be just one, or even none, or even more than one. So if you would like to attend using the neural network approach multiple relevant regions, you should combine multiple self-attention heads. It is also it can be also applied in NLP to let the network attend not only word level relationships, but also higher level relationships, just to do a composition aware attention. So at a higher level of attention. This is in intuition, okay, of how it works. This is the unit, the key, the core element of our network, which works exactly as I told you before. So it's dot product scaled softmax to get the attention weighting, and then you multiply by the weight the value in order to return the output of the search. Here you get you have a stack of multiple heads, and what you get is this, where this is no, not this. I would like to show you. This. We can see this here. Okay, we have multiple attention heads that can be combined together. Okay, so you can come up with a combination of the outputs of multiple self-attention heads, and this is the resulting softmax function. Okay, so you can do it hierarchical and multiple layers. Let me just go back just for a while. So the formulation, the mathematical formulation of the attention is basically a function that takes as input the query, a key, and the value. And you try to compute the similarity between the key, the query, and each of the keys, and you try to estimate which is the, of course, by combining the two, you retrieve the values you return the values with highest similarity. As I shown you before, this is actually a matrix, product of matrices. This is a graphical representation, which I think it's very effective, because as you can see here we have represented the text as using a JSON representation, as in NoSQL databases. So if the query is key 2, okay, I'm looking for this string. This string, of course, matches with one of the keys in the input data. The data can be represented as pairs key value. Of course, you have key 1, value 1, key 2, value 2. We have a lot of key value pairs. This is exactly like a content retrieval problem in information retrieval, or even in databases. The attention of a query returns, of course, the distribution of the, you will get the distribution of the keys with a probability. And of course, if you maximize the probability distribution, you find the probability that maximizes the similarity. So it returns value 2 as the most similar key according to the content of the query, which is key 2. Exactly. Now here we have an exact match. In practice, we may also have some partial match. So we can use, we can define, generalize using whatever kind of similarity matrix, a similarity function, or an edit distance using looking at similarities between two pairs of strings. So it's the choice of which similarity function you use is mainly dependent on computational issues. So it's arbitrary. You can redefine in your architecture the function in whatever kind, but of course then you have to cope with computational issues. So the cosine similarity is inherently simple because it's just a dot product. So you use it for this reason. Then you have the query here. You compute the dot product, the product between the query, which is a vector of position aware encoding with the key matrix, which are columns. Each key corresponds to a column vector. The product here is a product of row by column. So you get these numbers. Each of these numbers corresponds to the attention weight of a given key. So this is the similarity between a query and the key. For example, this number corresponds to the similarity between the query and the key number 2, which is maximal, okay? In this case, it's 1, of course. Here we have the probabilities because we have a softmax. So when you compute just the pairwise similarities between the query and each of the keys, you are not expected to achieve to return a probability because the sum is not necessarily 1. But if you apply softmax, then you get a probability distribution. Then you can multiply the attention weights with the values, which are row vectors, and return the values corresponding to the maximal, the key with highest similarity with the key with the query. So, to summarize the key advantages of this approach are that we miss the recurrent part of the network. We do no longer rely on a recurrent process. Okay, it works. We can focus on specific text portion disregarding the definition of a static context window. So with few training steps, we can compute in a highly parallel way all the attention weights using the self-attention idea approach and overcome in a very effective way the problems of vanishing gradient and the explosive gradient. You can facilitate, of course, the analysis of longer pieces of text or text with complex structures because you no longer have to define the local context manually of your piece of text. You can build, moreover, not last but not least, you can also build an explanation of your model. So whenever you apply such an architecture, you not only get the output. For example, for the sentiment analyzer, you get the sentiment score, positive or negative, of a piece of text, but also you can go back to the attention to the network, to the intermediate layers of the network, and look at the attention scores. So, for example, we will use as we will discuss later on in the following lectures. We can use, for example, BERT as a classifier to assign a category to a document, and BERT relies on the attention mechanism. There are solutions for exploring the way BERT attends to specific portions of text. One is called BERT Explainer, and BERT Explainer does exactly this. So look at the attention weights and try to tell you, okay, the network is a black box, is complex to you cannot look at into the black box because it's very complex, but you can indirectly explain what was the reasoning behind the network just looking at the attention distribution, because the attention tells you something about what are the parts of the network actually attends to. For example, a common graphical representation of this are called saliency maps, like this. No. Okay, these are plots used for model explanation, which leverage the attention information. So X and Y are words, as in the previous case, for the source and target sentences. For the self-attention, source and target are the same. You can also apply it not for the self-attention, but also for the attending other pieces of text in the same way. Each pixel, so each cell of the matrix, indicates the score, the value of the attention score. So you can color it in a saliency map as black for 0 and 1 for white. So of course, white cells indicate which are the items that maximize the similarity, like here. Okay, so of course, the main diagonal contains trivial similarity combinations because it's an item with itself, and the other are potentially relevant correlations. For example, here they have applied a saliency map for to an English to French translator. So when you have a translator that performs, for example, the encoder decoding for translating in English written piece of text into French, you have as a source a piece of text in France, and as a target the piece of text in English, and you see that the attention score is exactly what you need in order to attend the relevant portions needed for translation. So this is also a qualitative way to assess the effectiveness of your NLP model. In this case, a translator. Okay, here we can go fast because we already mentioned how to proceed. So in the encoder, we have the layers here. Okay, nothing special with respect to the previous architecture, so we can skip. Okay, we can output also the attention scores for providing explanations. The context vector we can generate for the neural machine translation is combined with the vectors generated by the hidden states, and of course contributes to the selection of the portions of text that are most relevant to decoding the translated version. So the attention hidden vector is used to predict which is the output at a given time instant. This is the function that we already know. Okay, here is the formulation. What I want to say now is that, of course, there is no a unique formulation for the attention. There are many different functions which can be used. You can choose which one is most appropriate for you. Here is a linear combination of probability and weights in order to get the output. But at the level of attention, okay, here it is. So given a query vector and a key, you want to find the value of the key maximizing the similarity with Q. So you compute Si as the similarity between Q and the Ki for every I. Then, in order to get the similarity function, the similarity score, you have many different ways. The most popular ones are additive attention, which is this one. The dot product, which is the most common one, and the scale product, which is the dot product with a scaling factor. What we reported before in the image was actually a scaled version because we normalize that value prior to applying the softmax. So the softmax is not included, okay? The softmax is standard. You decide which attention weight function use, and then you apply the softmax on top of the attention weighting scores. So the three main attention functions are additive dot product or scaled, which is actually a variant, a normalized version of the product. Any questions about this? During the next, not this, the next lab, you will also see an example of explanation based on attention. So we will show you how to leverage the attention score in order to explain. It's quite interesting because it's a simple yet powerful tool to get some hints on how a neural network model works, because neural networks have nice properties, nice performance, but are not interpretable at all. So in order to get some local explanation or global explanations, the only way is to open the box in some way. Attention scores are basically a way to capture local correlations. For example, they are used also for applications like identifying model bias or unfairness. When you want to understand whether the model is unfair with respect to a particular subset of samples, you can consider the content of a piece of text within that sample and compute the attention scores, because these reflect what was the inherent way the network represents the content of that particular cohort of samples. What happens typically is that there are some minorities in the data, there are some subsamples that are underrepresented, and this leads to model bias or unfairness. So in order to understand why and what are the kinds of documents that you need to provide in order to augment the data and to mitigate the bias and the fairness, you can use this kind of explainable AI models. Of course, similar approaches can be also have been proposed for image processing. Probably some of you already knows, for example, CLIP or some libraries which automatically detect, given an image, some patches. These kind of patches are relevant objects or regions in an image that can be leveraged in order to address some image processing task. So the idea is exactly the same, to compute the attention scores and then you reuse the attention scores in order to perform better, more insightful analysis. Any questions? Okay, so I think we can stop now, and we will meet later on next Tuesday. We will have a class practice on word and sentence embedding. On Thursday we have a lab, and on Friday we will talk about contextualized embeddings. Have a nice evening.